Okay. Okay. Interesting. Okay, so apparently I do not have permission to live stream, which we had tested everything up until that point. So unfortunately, I'll only be able to record this via Zoom. So to those of you that were attempting to join the live on YouTube, I'm very sorry that I am unable to stream this, but we will make sure that we make the recording available to everyone later. All right, so today it is my pleasure to introduce Dr. Som Dutt, who is going to be giving our seminar this week. And for those of you that are joining us live, you can go ahead and type any questions that you have in the chat and we will take those later. So Dr. Dutt obtained his bachelor's and master's degree from Kurukshetra University and his PhD degree from the University of Petroleum and Energy Studies in collaboration with the Wadia Institute of Himalayan Geology. He was awarded the Pose Fellowship by the government of Haryana, which is a state in India, in 2010. And since 2014, he has served as a scientist at the Wadia Institute of Himalayan Geology. His current research interests are to understand short-term fluctuations of summer monsoon in India using past natural archives such as speleothems and lake sediments, the natural forcing mechanisms and teleconnections to the Indian monsoon and their socioeconomic impacts on the regional society. And today he will be talking about short-term variability in Indian summer monsoon strength since MIS3. And with that, I'll go ahead and turn this over to you.
Thanks, Professor Kulhank, for the nice introduction. And namaste to all friends and colleagues for joining today's presentation. First of all, I would like to thank Professor Clift for having me in the Monsoon seminar series, which is a great platform to share, discuss, and learn about monsoon-related research work. In today's presentation, I will first give a brief introduction of the Indian monsoon dynamics, which will be followed by ISM fluctuation in northeastern India since MIS3. Northeastern India is one of the wettest places on the earth. And that part will be followed by late Holocene ISM fluctuations in northwestern Himalaya, in particular from the Ladakh region, which is a cold desert, which is considered as a cold desert at present time. And finally, a small discussion will be there about the regional variability of ISM fluctuations in the Indian subcontinent. So beginning with the Indian monsoon dynamics, we know the monsoon literal meaning of monsoon is the seasonal reversal in wind direction. Seasonal reversal of wind direction at a particular from a particular direction and at a particular time of the year. The fundamental driver of this monsoonal circulation is the land-sea thermal contrast. In particular case of Indian monsoon, during the boreal summer season, a low pressure zone is created between Indian Ocean and the Ganga Plain and western part of the Indian subcontinent due to land surface differential heating. And at the same time, the intertropical convergence zone, the ITCZ, shifted northward towards the Himalayas. And as a result, the cross-equatorial moisture-laden wind from the Indian Ocean enter to the Indian subcontinent from the southwest direction. That's why we call it Southwest Indian monsoon and also the Indian summer monsoon. These moisture-laden winds brings about 75% of the precipitation on an average in the Indian subcontinent. During the winter season, the low pressure zone from the Ganga Plain and the western part of the India vanishes, and the intertropical convergence zone that shifted southward to the southward of India into the Arabian Sea, Indian Ocean. And as a result, the wind started blowing from the Indian subcontinent to the Indian Ocean. And while crossing the Bay of Bengal, it gained some moisture from the Bay of Bengal and gave some precipitation to southeastern part of the country. These winds are relatively dry than the monsoonal wind during the summer season. For us in India, everything revolves around the monsoon. Here, the monsoon has become synonymous to the summer season rainfall that is more than 75% in most of the part of Indian subcontinent. So give dire effects on the socio-economic condition of Indian subcontinent. The role of Indian monsoon is very critical for food and water security of the region of South Asia and Southeast Asia. More than 3 billion people live in this region, and food or water security is a critical matter for this region, as well as with the growing global conflict and the climate change. This needs to be, its importance is increasing. The monsoon rainfall in India controls the snow cover at the third pole, which is Himalayas. Himalayas have a highest snow and ice coverage after the north and second pole, and that's why it is also considered as the water tower of Asia. And this is mainly controlled by the Indian summer monsoon. Most of the rivers in India and neighboring countries maintain their flow by the precipitation or rainfall received by the summer monsoon season. Groundwater and spring recharge is also also mainly controlled by the precipitation by the Indian monsoon. And 50% of India's GDP, which is mainly by the agricultural product, is directly controlled by the monsoonal precipitation and related irrigation facilities. So with this much importance, that's why we are trying to understand monsoons since ages. But although this monsoon phenomena is a regular phenomena, it is very unlikely to have similar or same rainfall in 2 consecutive years, because it is dependent or controlled by several external and internal monsoon dynamics on various time scales, starting from the intra-seasonal to the tectonic time scales. Some of the controlling factors or influencing factors are written here, and their response and relationship is non-linear. That's why to understand the forcing mechanisms and teleconnection to the Indian monsoon, we must need the long-term records of rainfall variability in Indian subcontinent, which is unfortunately we have the data coverage of up to 150 years only, and to gain or to reconstruct higher longer records, we have to rely on the proxy records, so that we can understand the influencing factor or forcing factors or teleconnection to the Indian monsoon at various time scales. For that, we use the paleoclimatic archives, including marine archives such as Globigerina borealis, foraminifera, and river discharge in Arabian Sea as well as Bay of Bengal. Similarly, we use continental archives of like glaciers, rivers, lakes, speleothems, tree rings, and peat bogs. In the earlier part of, for a long time, we used marine archives, which were mainly related to the wind strength. and river discharge for reconstructing the past monsoon variability. But now this trend is shifting, and more records are coming from the continental archives. The reason of this shifting towards the continental archives have these continental archives have many advantages. We can have higher resolution of using the continental. We can even get annual to seasonal scale variation of Indian monsoon or rainfall or climatic changes using the continental archives. Wind strength in Arabian Sea is not always linked with the rainfall in Indian subcontinent, and within that also wind strength in may be linked to some part of the country, but in another part of the Indian subcontinent this may not reflect the actual rainfall condition. Further, the role of Arabian Sea and Bay of Bengal branches in receiving the precipitation on the continental parts is not much explored. Also, the flood and droughts. These are the continental phenomena. The impacts of flood and drought are received on the continental parts, and that affect the socio-economic condition and relate the human climatic interaction. If we want to know about the effect of climate change on any society, for example, the human settlement or human migration, we must prepare the records of paleoclimate from that particular area only. And the oceanic part mostly represent the average signal for a large part of the landmass. And for human climatic interaction, we must reconstruct the climatic history for the targeted areas. So in the same trend of shifting to monsoonal studies to our continental archives, we have used the stalagmites samples from Mamlu, Omsring, and Vasikar caves to get subdecadal to sub-centennial scale monsoonal variation in northeastern India. These speleothems are deposited by the degassing of CO2 in the caves. What happens actually, when the meteoric water percolates through the soil zone, it interacts with the soil CO2 and form carbonic acid. That carbonic acid further percolate downwards, and when it reaches the ceiling of the cave, where the partial pressure of CO2 is less, then CO2 degassing occurs, and as a result, the calcium carbonate from the solution came out and precipitate in various forms of the speleothems. We use mostly stalagmites to avoid any chances of age reversal. Some other advantages of this speleothem are these speleothems have the capability of getting accurately dated using uranium series dating. We can achieve seasonal, annual, or such kind of high resolution using the proxies of speleothems like lamination counting and the oxygen isotopes. Oxygen isotopes of speleothem is mainly linked with the regional precipitation. So in speleothems, we use proxies of oxygen and carbon isotopes, then elemental proxies such as magnesium and calcium ratios and strontium and calcium ratios, and then the reflectance, then architecture element of the laminations, and then the petrography. But in today's presentation, I have used the 18O of speleothems from Northeast India only to get the signature of regional precipitation. In Northeast India, there are massive and there's a widespread karst network and beautiful limestone speleothem deposits in various forms. We have stalactites, stalagmites, columns, straw, and these speleothem track the oxygen isotopic signature in these speleothems, track the changes in the moisture sources, track the changes in the meteoric precipitation, which in itself is linked with the changes in moisture source, then distance traveled by the moisture, and partly by the amount effect, in such a way that more enriched oxygen isotope value in speleothems is linked with the reduced monsoonal conditions or low monsoon conditions and lesser rainfall in the region and surroundings. And the more negative values of oxygen isotopes are linked with the higher precipitation in the region and around. So with this background, I'm sharing our first record. This was our first record from the Mamlu cave. In this Mamlu cave, this was our first record from the Mamlu cave. Here we can see pronounced changes in Indian monsoon strength between 33.8 and 5.5 kilo year BP. We can easily see the positive excursion of oxygen isotopes during the Henrich events and younger dryas. These were the and higher precipitation during boiling Alaroid and early Holocene interval. We can say here that the warmer intervals were linked with the higher precipitation or strong summer monsoon condition, whereas the colder intervals and were associated with reduced monsoon in the northeastern part of Indian subcontinent. We see here LGM was not much reflected in terms of reduced monsoon condition in here in the region, and the minimum rainfall occurred during the Henrich event 1. We can also observe here a synchronicity and asynchronicity of Indian monsoon with that of Chinese records. Just from here around 17 kilo years BP, there is a just from here to younger side, from 17 kilo year BP, there is a synchronicity of between Indian monsoon and East Asian summer monsoon, but that is not the case prior to that time frame. Our record also matches well with the Bay of Bengal salinity record. The salinity was lower during the early part of the Holocene. It was higher prior to the Henrich event, prior to the boiling Alaroid time interval. When we plotted our record with that of solar changes and the data from the GISP2 record, we can easily say that orbital scale changes of the Indian monsoon were more were regulated by the changes in the solar insolation, whereas centennial to millennial scale changes of Indian monsoon were more controlled by the changes in North Atlantic. The excursion in cooling period of North Atlantic are aligned here with the reduced monsoon condition, and the signal of North Atlantic cooling is transmitted to the Himalaya through the mid-latitude westerlies. We further extended our record towards the older time frame till 46 kilo year BC. We can see here the interstadial signal which we call Dansgaard-Oisker cycle. The interstadials 1 to 11 are beautifully visible in our records, which again testify and authenticate the warmer intervals are associated with stronger monsoon in India, mainly by the increase of land-sea thermal contrast. And the signal of North Atlantic and the high latitude northern hemisphere forcing is also visible here during the weaker intervals. One more striking feature in this record is the younger dryas. A sharp decline of the Indian monsoon during the younger dryas and then an abrupt recovery. Almost similar results are visible in some another record from the same area, from the Umsring cave record. We have a clear-cut decline in the Indian monsoon shed during the younger dryas period. The same kind of condition were also observed from the Timta cave, that is in the northwestern part of the country. So we can say the effect of younger dryas was quite evident in most part of the Indian subcontinent, especially the northern areas. Now coming to the younger records, this is another record from the Mamlu cave showing the ISM changes between 200 BCE to around 1986 CE. We can see here from 200 BCE to around 360, moderate kind of monsoon conditions were evident, and thereafter at around 400 to around 1060, above average rainfall received due to the stronger monsoon condition in northeastern part of the Indian subcontinent. And after the 1060 CE, there is a clear-cut decline in the monsoonal precipitation and the lowest rainfall received during the modern minimum period. With this graph, we can say the first millennium CE received higher precipitation than that of the second millennium CE. Further, the medieval climatic anomaly that lasted up to around 1300 or 1350 CE. The later part of MCA was not that much wet, which we considered earlier. In northwestern part of the country, as well as central part of the country, it is around 1300 CE that higher precipitation received, but in northeastern part it was 1060 CE and rainfall got reduced thereafter. Then we try to find out the controlling factors and the reasons behind it. So we see here the latitudinal positioning of the ITCZ. When the ITCZ positioned more northward, the precipitation was higher in northeastern India, and when it shifted southward or positioned southward, the precipitation got reduced. And the period of the modern minimum matches very well. We also see here a very good match with the Arctic temperature that I earlier discussed, the northern hemisphere high latitude forcing to the Indian monsoon. Here, whereas the temperature was higher, the monsoon was stronger. And right at around 1060, which was the period then the decline of the monsoon precipitation started in northeast India. the same time, the temperature of the Arctic started reducing. So it further indicates that on centennial scale to millennial scale, Indian monsoon circulation is affected by the North Atlantic and in that area. We also tried to find the regions of these sudden positive excursion in delta 18O and linked to the monsoonal rainfall reduction. We see here these events are well correlated with the high volcanogenic sulfur loading in the atmosphere. Due to high volcanogenic sulfur loading, the atmosphere got cooler, and as a result, the low pressure zone in India could not be stronger, and the monsoon circulation and convective activity got reduced, and this part of India received lesser rainfall. We have another record of high resolution. It is having a quasi subdecadal resolution of last 900 years from the nearby cave, that is Vasikar cave. We can see here three different time zones in the Little Ice Age. We earlier considered the Little Ice Age was a prolonged arid event because of the climatic cooling. But here we can see it has three different time frames. In the first part, we see the high two episode of very high or very strong monsoon condition and higher rainfall. In the second part, the monsoon condition was moderate and rainfall was close to average, and the changes were more secular than the first and third part. No abrupt changes or less abrupt changes are recorded during the second part of the Little Ice Age. In the third part, when after the Industrial Revolution, the atmospheric temperature started rising, we again see the increasing of the monsoonal circulation and rainfall in this part. Also, the changes are quite abrupt. Very frequent high and low, strong and weak monsoon conditions are observed during the last part of the Little Ice Age, and the same trend continued in the current warming period. When we try to find out again the controlling mechanisms of the Indian monsoon condition during these 900 years, we see here these fluctuations of very weak monsoon or reduced monsoon conditions are linked with the solar minima. This is Wolf minima, sporal minima, and Maunder minima. These were the intervals when the sunspot activity reduced drastically, and this was also associated with particular in these regions with this high volcanic activities, volcanic activities and high volcanogenic sulfur loading in the atmosphere induced cooling that was further amplified by the less solar activity or sunspot activity, and we receive lesser rainfall in northeastern India. These changes has several socio-economic impacts on India. These were the intervals where the large empires in here are collapsed and disintegrated into several small states. Because of the lesser rainfall, fight for the resources started first, and discontent in the public arises, and as a result, the larger states disintegrated into smaller states. Now coming to the late Holocene ISM fluctuation in northwestern Himalaya. So I have used the Somrari lake. We drilled a core and we prepared a multi-proxy record from the Somrari lake. This is our record. The EM2 score is showing the high energy flow. EM3 and EM1, these are the low energy flow. This we see here it around 4.3 kilo year BP. There is a drastic reduction in the high energy flow. That is also reflected in the lesser weathering and erosion in the catchment of the Somrari lake. So we have linked this with a drastic reduction of Indian monsoon conditions in northwestern part of the Himalaya. This drastic conditions was not only in the northwestern part of the Himalaya. The same reduction in the monsoonal precipitation is also evident in several other records. This is the record from the Arabian Sea, and this is the Mamluk Cave record. This is the record from the Haryana plains, and this is the record from Somrari lake. So we can see here a pronounced weakening of ISM, and that led to the precipitation reduction in northwestern Himalaya. Although the timing varies here in the records, and this 4.2 kilo year event and the related dry period led to the displacement of Indus civilization in India. The main reason behind this 4.2 kilo year event was mainly the high intensity of El Nino that started rising at around 4.3 kilo year BP and gain its maximum intensity at around 3 kilo year BP. At the same time, the ITCZ also shifted southwards. So El Nino influenced the Indian monsoon condition in western part of the Indian subcontinent and led to the lesser snow precipitation, and as a result, the river discharge decreases in the Indus River and its tributaries. That led to the displacement of Indus civilization. This is a pattern of Indus Valley settlements. During the mature Harappan phase, the blue color indicates the mature Harappan phase, whereas the late Harappan sites, now people started migrating towards the southern and southeastern part of India to get more water resources. In the earlier part of the mature Harappan phase, they developed some water harvesting structure and also used drought resistant millet varieties, but with a continued decline or continued drying phase, they could not cope up with the nature and had to are forced to migrate towards the southern and southeastern part. Now coming to the last part of the presentation, it's the regional variability of ISM fluctuation in the Indian subcontinent. So this is a review of Holocene climatic fluctuations in India. We can see the most of the proxies shows a gradual decline from gradual and a regular decline from early Holocene towards the late Holocene in terms of precipitation amount. But this in the Lonar Lake data, in the middle Holocene, a sharp decline in the rainfall occurred that lasted for more than a millennia, which is not evident in any other record. The same event is also reflected, somewhat reflected in northeastern part of the country. So we have come to know that there is a certain regional variability in Indian monsoon dynamics. We can also see the similar pattern in the popular 4.2 kilo year event. We can see here in the peninsular India, there was a prolonged drying up for around 500 years, but which was not the case in central India. With the Lonar Lake data shows a gradual decline or almost no decline in the precipitation. The Mamlu cave, which has the credit of giving the new age in the geological time scale, the 4.2 kilo, it started around 4.0 and that lasted for around 200 years only. Lake in the Sikkim shows a sharp decline for a prolonged period and the lesser precipitation. Lake records from northwestern India also shows for a prolonged time the monsoonal conditions were weaker and the region received lesser rainfall. Here in central Himalaya, we can see here the Lake Rara from Nepal. We have a significant reduction in the rainfall, but which is not the case in caves from Uttarakhand. Again, the Western Himalaya received very less precipitation during the 4.2 kilo event. So there is regional disparity that occur in the monsoonal circulation and monsoonal precipitation in various parts of the Indian subcontinent. We can see the same here, as I discussed earlier. Northeastern part of India shows a decline in the precipitation right after 1060 CE, but which was not the case in central India and northwestern part of the country. In later part of the medieval climate anomaly, the precipitation was higher, but in northeastern part, it got reduced. We can observe here also for the last 900 years, we can see here the northeastern part received a gradual moderate rainfall during the middle part of the Little Ice Age, but the northwestern India and the central India, it was quite lower rainfall. In the paleoclimatic proxies, we can say that these changes or this regional variability may be because of the proxies response or the age uncertainty. But this is the record of regional variability of ISM fluctuations or ISM rainfall fluctuations during around last 120 years. We can also see the similar variability and regional disparity here also. We can see here during the period between 1920 to 1970, the northwestern part, west central part, central northeast and northeast India received higher precipitation, whereas the peninsular India received lesser precipitation in some part and higher precipitation in later part. So we can say that there is a regional disparity in Indian monsoon rainfall that exists, and to cater that, we have to prepare more high resolution records from continental area to get a better picture of past rainfall conditions, and so that we can make our predictive capabilities better. So with this is the summary of today's presentation. The strong ISM conditions existed during warmer intervals of bowling Aneroid early Holocene DO events, and weakened ISM conditions during intervals of Henrich events, younger dryas, and so on. A close alignment of cave date 18O in northeastern India with the GISP2 record suggests high latitude forcing of the ISM on centennial to millennial scale. The millennial scale ice volume and sea ice signal from North Atlantic is transmitted through westerly mediated mechanism. A pronounced regional differences exist in ISM fluctuation in Indian subcontinent, which is quite evident during the Holocene. The 4.2 Ka event was associated with the reduced rainfall in Indian subcontinent. Reduced rainfall conditions prevailed for around 200 years in northeastern India, whereas it protected for around 500 to 1000 years in northwestern part. The weakening of ISM during 4.2 K event caused the migration of Indus Valley civilization. No climatic interval was completely dry or wet. Middle climatic anomaly had multi-decadal droughts-like conditions, and very high rainfall episodes were observed during the Little Ice Age. Solar forcing, ENSO, latitude positioning of ITCZ, and volcanic eruption are major controlling mechanisms on subdecadal to subcentennial scale. Abrupt rainfall fluctuations are more evident during warmer intervals, and colder intervals are aligned with more secular changes. Frequency of extreme events may increase in Indian subcontinent because of increasing global temperature, leading to higher land sea thermal contrast and more higher convective activity. More high resolution records are needed from continental areas for making a comprehensive model of past rainfall variation and future predictions. That's all from my side. Thank you. These are the people which have contributed in these research work. I would like to acknowledge all of them. Thanks a lot.
Wonderful. Thank you very much for that very interesting talk. Do we have any questions from anyone in the audience? You can either type them in the chat, or if you want to raise your hand, then you can unmute and ask your question. And while we wait for those in the audience to think about their questions, I actually have a question for you about your comparison of your cave record to the GISP ice core record. Could you go back to that slide? It was very near the beginning of your results section. Sorry to make you go all the way back.
No, that's fine.
Yeah, it was back a little. It was one of the first couple of slides when you were showing your results. Maybe.
I think this.
Yeah, yep, that will work. So there's a really good correlation between the two records after about 25,000 years ago, but then you kind of see that it looks more decoupled before that. And I'm just curious if you think that there's a change in the forcing mechanism, or if you think that maybe there's an offset in the age models.
Mostly this may be because of the age model. Actually, we have only one age here. After here, we have only one age, that is reflective. If we have more ages, may possibly it's the same pattern which we are observing after 25K.
Great, thank you. Yeah, I was just wondering because it did look like maybe there was just an age model issue, and that would definitely make sense if you don't have very many age points. Does anyone in the audience have any questions? Otherwise, I have one other quick age model question. I was just curious for your lake core record that you showed for the last few thousand years. What is the age model for that based on?
The age model was based on the carbon-14 dating of lake sediments. It was bulk.
Wonderful, thank you. Was there pieces of wood, or did you have other just pieces of other material that was dated? I'm just curious what was being carbon dated.
It was mostly the bulk lake sediments.
Okay.
For the very recent time, to calculate the rate of deposition and so on, we use cesium 137 and Li-210 also.
Ah, cool.
But for the upper parts only.
Mm-hmm. Great, thank you. All right. Any other questions from the audience? Otherwise, Dr. Dutt, I want to thank you again for giving us this very interesting seminar. And with that, I'm going to go ahead and stop the recording.
Thank you, Professor Kulana.